We've been talking about stoichiometry and what this process actually is, and simply put, stoichiometry is just a way it allows us to not only measure the elements, but really predict the amount of product we can get in a reaction. So atoms and molecules are incredibly small things, and it's really hard to use tools to measure their exact amount. And so we use processes of converting those into more manageable numbers, into which are more like grams and kilograms and things that are a lot easier for us to handle, and on a scale that we actually typically will perform a reaction. Before we can jump into stoichiometry, the first thing we need to understand is the AMU, how to find it, what is it. So AMU stands for atomic mass unit, and an AMU really we've just known as now as an atomic mass. That's the atomic mass, and we just have really said that's what it is. We haven't really gotten any further than that besides just knowing it and knowing how that affects isotopes and all those things. So remember, we can find that atomic mass just underneath every single elemental symbol, right? On most of our periodic tables, that's where we're going to find it. When we're finding AMU2, you can leave all these decimals if you want, or you can round to the nearest whole. The only time you're not going to want to round to the nearest whole is if you have something like chlorine, in which it's pretty much in the middle, and so then those decimal points can be kind of important. But if it's really close, like if it's nitrogen or hydrogen, any of those, we don't need to worry about it too much for our purposes. If we need to be more specific, I'll make sure to specify that in the question or whatever problem we're working on. So our first question that we have, so we have to find the AMU for these couple of compounds we have here. And so the first one is our oxygen, and it's got two of them because we have this subscript. And so what we have to do is we'll look at our periodic table, we see, okay, that atomic mass of one oxygen is 16. Now we have two of them, so it's really 2 times 16, or you think of 16 plus 16. And then if we do that, right, then we're going to end up with 32 AMU. All right, and now continuing forward, if we have our now CH4 here, then we can look, okay, well, carbon's going to have 12.01, hydrogen is 1.008, and we can just call carbon 12 and hydrogen 1. And so with 4 hydrogens, that makes the hydrogen part have an atomic mass of 4, and the carbon being 12, so it's really 12 plus 4, which is going to give us 16 AMU. And as we move right along, if we have our now calcium chloride, our ClCl2, then we can find our calcium over here, and that's 40.08, and we can call that 40 if we want, and we have our Cl, which is that 35.45, right? So that's kind of important to leave that there, so then we can write that out. And we're going to end up getting that, well, let's see, we have 2 chlorines, so we have to make sure we multiply that by 2, and then, which is going to basically give us to be 71, right? And then we have our calcium at about 40, so 71 plus 40 is going to basically give us 111 AMU, right? So make sure we don't forget. A lot of people forget if these subscripts are like, oh, well, I can see calcium chloride or the same thing hydrogen, then they're going to be a little bit off. So make sure we have those 2 chlorines in this scenario because it's bonded with 2. Alright, so the next thing that we have to talk about before we get into some more of those calculations of stoichiometry is going to be the mole. And now the mole, what's really awesome about it is the mole allows us to take the measure of an atom and convert it into grams. So we just talked about we have this atomic mass unit, but what is that, right? We don't know how to measure that per se. We don't have, a scale calibrated to an atomic mass unit. It's something that we just made up to represent it. All right, so then we now have this wonderful thing called a mole. And so a mole is 6.022 times 10 to the 23rd, right? So it's a huge number of anything. So the mole is a unit, and as with any unit, it represents a certain number of something. Just like centi, means 100, right? So a centimeter, there's 100 of those in a meter. Okay, so that unit represents a certain value, and a mole is representing that 6.022 times 10 to the 23rd, and that's of anything. For our sakes, that's always going to represent the number of molecules of something. So if I have, 1 mole of calcium, then that means I have 6.022 times 10 to the 23rd molecules of calcium, or atoms of it. Okay? But as I mentioned in class, we could have that number of pineapples, or grains of sand, or really any of those, which is just a whole bunch, right? So the nice thing then about a mole is that it's super easy to convert the AMU on our periodic table into moles. It's really, really easy. So for example, carbon-12, so the most abundant isotope of carbon, has an AMU of 12. Okay, 1 mole of carbon-12 is 12 grams per mole, meaning for every mole, so for every 6.022 times 10 to the 23rd atoms of carbon, it's going to be 12 grams. So if you have this many atoms of carbon, it's 12 grams. Okay? So in other words, right, that 6.022 times 10 to the 23rd molecules of carbon is 12 grams for every mole. So if I had 2 moles of it, it'd be 24 grams. If I had 3 moles of it, it'd be 36 grams. And so this makes it a lot easier. It's a lot easier to measure the grams of something. It's kind of in a more physical measurement, a physical unit that we can actually use. So the biggest thing when we're switching between AMU and moles is we just change the unit. Okay? And in this case, we have grams per mole, because that's the amount of mass we have per mole. Okay, so while the number stays the same, we just switch it over. So if we go through and look at these exact same compounds that we just had, and now we're looking to find the molar mass of these things, right? Then all we got to do is we look at the periodic table just like we had before. Okay, and we have the number of atoms that we have in each one, right? So we have 4 hydrogens, 2 oxygens, depending on which one we're looking at. The big difference here now is we're going to have grams per mole. So whenever you see molar mass, your unit's grams per mole. Okay, so if we do that, we have our oxygen, so it's going to be 32 grams per mole. If we go to our CH4, it's going to be 16 grams per mole. If we go to our calcium chloride, it's going to be 111 grams per mole. What you should have noticed by now, and I've kind of been hinting at, is, right, so our AMU, our numbers, when you found each one with their molar mass of these different compounds, they're the exact same. The only difference is these are now in grams per mole, and these are in AMUs. This is something that we can use a lot easier. These, not so much. So that's why this step is really, really important, and you will be using it many times to kind of set up our questions that we have. The next piece we got to talk about is total mass. So we can find the total mass of a substance in a reaction by multiplying the molar mass, again that's grams per mole, by the number of moles of that substance in the reaction. So for example, so we have this reaction, okay, right here. And now remember, the number of moles in a reaction, something I want to make sure we highlight here, is represented by the coefficient. So we have right here, and then if we don't have something here, we kind of assume that it's the number 1, and then number 1, and here we have 2 again. So in this case, right, so that means 2 moles, okay, and in this case, that means 1 mole. All right, so as we move forward here, so the molar mass, if we want to find the total mass of this reaction, first find the molar mass. So the molar mass of KOH is 31.9 plus 16 plus 1, right? So that's for all of these things. And I just left that decimal here. You could have made this 32. I just left it to be a little more specific, which gives us 48.9 grams per mole. All right, so that's telling us for every number of mole we have, that's the number of grams. So now we want to find the total mass. So in this reaction, if we were to measure it out, how much mass of this potassium hydroxide, this KOH, would we have? Well, the total mass of KOH in the reaction we have, so to find it, we take 2 moles and we multiply it by our 48.9. Now if we do that, what ends up happening as far as units go, these cancel out. Okay, and that's how we're left with just the grams right here, because you could think of it as 2 mole over 1 times our 48.9 grams over our mole, right? So if that happens, then these get crossed off. If you kind of think of cross multiplication, then we're left with our 2 times 48, right, which is then going to give us our 97.8 grams, as that is the only unit left over. Alright, so now that we've covered all of that pre-information here, let's actually use the scenario in which we might want to actually use this. So I always think of a chemical reaction as essentially a recipe. Okay, if you're baking cookies or something, you have a recipe and it tells you, okay, well you should expect, or this will serve 4 people, or it'll make you a dozen cookies, right, or whatever it might be. It gives you some sort of measure of your product. Well, that's essentially what our chemical equation is doing here. It's just with chemicals, okay, and essentially cooking is chemistry. So with the same reaction here, I want to know, so if I want to perform this reaction, if I have 85 grams of our potassium hydroxide, again, KOH, assuming I have excess of all other substances, so that means that I have more than enough of everything else. This is the only thing that is kind of limiting my reaction. And we'll talk about limiting reagents a little bit later. How much water will I have left over as a product? So I want to know, how much water am I going to get left as a product? What will I get? That's what I'm curious to know. And now, I want to know this before I do the reaction, because maybe I want a certain amount of water. I want to know, will I get enough? And so that's what I want to do before I do the reaction, right? That's the key piece there. So, if we're doing this, my first step is going to be find the total mass of 2 moles of KOH. Okay, so I got to find the total mass of this piece. That's what's really, really important. Because I want to know basically, what is the recipe actually calling for? How many grams does my recipe actually want me to find? Okay, because remember I have 85, how much does my recipe want me to have? So if I do that, then I find that 2 KOH is that 97.8 grams. So in the reaction above, it's 97.8 grams. So that's what my recipe calls for. That also means I have 85 grams. I know that I'm going to be a little bit short, which means when I get to my final answer of knowing how much water I should have left, I should get a number that's a little bit less than what this reaction is asking for water. If I get a number that's greater than it, then I did something wrong somewhere. My step number 2 is to set up the ratio of the actual divided by the reaction value. So the actual being the number from the question. I actually have 85 grams. Okay, so that is my actual. And then from the reaction value. So my reaction value is right here. Okay, so that's the reaction. So I got to set up that ratio. If I set up that ratio, then I'm left with 85 grams divided by my 97.8 grams, leaving me 0.869. You should not have a unit here because our grams will cancel out. Because, again, it's a ratio, so we should have the same units. They need to be equivalent as far as that goes. So we cross those out, and so that's why I do not have a unit here. Ultimately, if you mess that step up, it's not the end of the world in the sense that your number is so correct, but your units are wrong, so you're technically reporting the wrong thing. Our third step that we have to do is we have to multiply now that ratio to the total mass of water, and again, H2O, in the reaction. So again, that's total mass, so that means we got to find 2H2O, the total mass of that, and we multiply it by a ratio, right? So this ratio that we have up here is really telling us that we'll have 0.869 of the actual, and if you converted that into a percentage, it would be basically 86.9% of water is what we'll have for the reaction, right? So, if we do that, we have our 0.869, and we're multiplying that by our 36 grams, because that's our total mass of our 2 water molecules, or 2 molar water molecules, I'm sorry, or 2 moles of our water. So that gives us our 36, because each one's 18. And so if we multiply, we get 31.284 grams. So we get just over 31 grams of water. So say I only needed 30 grams of water, then I'd be good. If I needed 40 grams of water, then I know I need to get more of my potassium hydroxide in order for me to get a successful result from that reaction. Alright, so we just did the one where we're finding the mass, so the actual measurement amount. Now what if I just want to know the number of moles I need? This can be important because sometimes you'll get chemicals reported in the molarity, or the number of moles that they are. So maybe I have 2 molar of a solution. What if what if I actually need 3 moles? The reaction with it. So then I need to, mess with concentrations and things like that. So sometimes it is important to find the number of moles. Now finding the number of moles can usually be a lot easier than with the actual mass of the substances, because there's just a lot less stuff you have to go look up, and we can simply just use our balanced equation. So if we're doing that, we follow the same pattern in which we say, okay, how many moles of water are used in the original reaction? Again, we're looking at, okay, how much does our recipe call for? And this time, we're just looking at moles, not the mass, all right? So we don't even really need to go look at a periodic table. So all we need to do is like, okay, so in the original reaction, how many moles of water were used? Because so our question is, I have 3 moles of water as a product from the below reaction. How many moles of potassium hydroxide were needed for the reaction, assuming I have excess of all the reaction, or all other substances, right? So we got 3 moles worth of water at the end of the reaction. We want to know, okay, how much of that potassium hydroxide did we just use? So in doing such, we can say, okay, well, in the recipe, it calls for 2 moles. We used 3. All right. So moving right along, we have our 2 moles. Just as before, our step 2 is going to be setting up the ratio, again, of the actual divided by the reaction value. Okay, so again, actual being what we used up here, and our reaction value being, well, right here or right here for our water. We set up that reaction, we do 3 divided by 2, again, those moles, mathematically wise, will cancel out because they're the same unit being divided, so we're left with 1.5 as our ratio. Then we need to multiply that ratio to the number of moles of KOH used in the original reaction. Again, we're not worried about the total mass because we're not looking for that. We're looking for the moles. Well, we originally used 2, so that means we're going to have to take 1.5 and multiply by 2. That leaves us with our 1.5 times 2 at 3 mole. And now if we logic check this, we think, okay, does this make sense? Well, we originally needed 2 moles of water in this reaction. We used 3. Well, assuming that this was the smallest quantity, or, well, that's what we got, so we know we can't have more of anything else, right? So assuming that, at a minimum, we needed to use 3 moles of potassium chloride to get to that point. We maybe used more and something else was eliminating our reaction, but at a minimum, we needed 3 mole of our KOH to get that amount of water. We needed more than just this 2 to get there. And it makes sense that they're actually the same amount because we had 2 moles on this side, 2 moles on that side. Remember, it needs to stay balanced. We're not magically creating more matter, which means they need to stay the same ratio to each other. So it's always nice to go back and kind of logic check it. Does that number make sense? And with this one, you can kind of logic your way through and say, oh, well, because of that, then that means this must be 3. Not all of them will be that easy where you can just kind of look at it quick, but some of them absolutely will be. That ends our video lesson on stoichiometry. If you have any questions, please let me know, and I'm happy to help you out.